All right, so as I mentioned, we're going to go over PCB layout techniques using Eagle, and we kind of already discussed the topics that we're going to look at: component placement, defining ground pores. We'll look at Eagle's design, or the DRC tool, which allows you to specify the design rules for a board. Check out the AutoRouter. What are its settings? How to use it efficiently? What are its limitations? Things to avoid. We'll look at doing incremental routing and ripup, and and also defining some net classes. How to use that. Once we've covered these things, that'll be most of the work in defining your board and doing a layout. After we're happy with our design, we can go and take a look at the CAM processor, which is Eagle's tool for generating Gerber files. And then after we've generated those, we'll look at a Gerber viewer to check to see that our files were generated correctly. So let's start by looking at component placement. And let's see. To facilitate this tutorial, I'm going to pull up a design that I worked on a couple years back, and we can take a look at the schematic first. It's an audio line level audio mixer, and this has a couple of inputs, an input stage, uses some low noise op amps. In fact, the 275s that this is one of the parts that I recommended for using on your headphone design. Uses a low noise chip from Analog Devices, the SSM2141, which is an instrumentation amplifier, and has a gain stage and a summing stage, and that feeds off to a main mixer stage over in this area. And these are the output drivers, which drive line level signals as well. The system also boasts, a very simple headphone amplifier. So take a look at this is a different approach, an op amp based approach, very different than what you're going to work on. And you can see that you can go for a design like this. You notice that the amplifiers are summed in parallel to increase their drive current, whereas you're using a discrete based output stage with push-pull large signal transistors, or I should say higher power transistors to drive the headphone coils. All right, and then there's a power supply. And so for this schematic, there's a board which I already have laid out. Okay, so we won't go through the process of looking at placing things. You've had a chance to look at that a little bit, but the first thing I want to look at is component placement, right? So the way that this board is laid out is that these are Jack 1 and Jack 2, or J1 and J2 are the input jacks left and right, and that's where the signal enters the system. So what should be closest to them is, well, of course, it should be the input stage circuitry, right? So let's look at J1, the left channel. It first meets C2 and C3, R1 and R2, and these these OP275 op amps, U1A and U1B. Okay, so just to give an idea, that's what I should see when I look over here. So then I've got C1 and C3 or C2, R1 and R2, and U1, which the OP275 is a dual op amp. So U1A and U1B both reside in this. Okay. Now there's other components you're seeing here that I didn't list or didn't show here, and those are some of the other components associated with the input circuitry. Okay. So what the thing to point out is that this is where you want to pay attention to the flow of your signal path on the board as well, right? Try and minimize the distance that signals have to travel. So the general flow of this setup is that things run from the input jacks through sort of the input stage, then hit some. I think this is the. Let's see, is this the differential amplifier? This is the differential amplifier for the left channel. This is for the right channel. the gain. Okay, there's a gain stage, right? Remember, the gain stage interfaces to this 20 kilo ohm potentiometer. Okay, that's the gain control. So that sits on the outside of the board by design. And so there's the potentiometer for it sitting on the outside of the board. So it makes sense that the gain amplifier, the op amp for this, is placed nice and locally to the gain potentiometer. Okay, what are some of the other parts that I'm seeing around all these op amps? You'll notice that I've got capacitors around all the op amps, even the op amps that don't show any caps around them, like U8A. This doesn't have any caps around it, but when I look in the board, U8A, that's what's driving the headphone amp, and that's, where is it? Here's a good technique for you to learn, is you can, if you type the word show and U $8, it'll light up. So if you're looking for a part in the board and you've got a lot of things all over your board, you know what you're looking for from the schematic, use that command. Just type in the word show and then the name of the part you're looking for. So you'll notice that it has a couple of caps next to it, C27 and C28. Okay, so what are those doing there? Well, those are the bypass capacitors. Starting with the BJT lab, we'll start looking at the use of using bypass capacitors. Has anyone ever heard of using that before, or a little bit here and there? They're capacitors that are intended to locally stabilize the power supply levels at ICs. So in general, you typically place these just next to the power supply pins on the ICs. So we were looking at, it was like C27 and C28, and here's the power for U8A here. And so yeah, it's just running from the plus 15 rail to ground, and from the minus 15 rail to ground. Okay, and those are just bypass capacitors. Okay, you're going to be using some of those in your design. They're actually already placed on the schematic that you're going to use. The idea with them is that they should be placed locally to the op amp supply pins. So when I check here and say show this line, well, okay, look at that. I typed in show. I click on this. It'll show me everything that's connected to this net, and this net is, if I look down here, it's plus 15 volts. It also tells me what class it is. We'll take a look at that in a second. But that's the point being is that the capacitor is placed very locally to the op amp supply pin. Okay. So that's a bit on component placement. I believe the next thing we were going to look at was defining ground pores and using the polygon tool and naming things like that. So if we jump back over to Eagle here, you'll notice that I actually have two ground pores on here, and that's not something you're required to do. You just need to do one. I'll tell you a bit about why I did two. It's a noise rejection scheme. A lot of times when your device goes into a chassis, you route the ground cables that come from devices that are interconnected, which come in on the sleeve of a TRS jack. This is a tip ring sleeve jack here. And so the idea is that noise can be, you can create ground loops between interconnecting equipment that are far away. Okay, and through various methods, 60 hertz noise can travel on the ground conductor, on the sleeve of your interfacing cables. And the thing to do is to recognize that it's going to be there. It's unavoidable. Certainly for longer cable lengths, it's unavoidable. And the reason stems from the fact that wires have they exhibit non-zero resistance. So when you plug into ground at one end of the room, and then you run cabling from there over to another end of the room, the ground conductors, because it carries return current, has a small voltage drop across it. And the return current is AC. it's sinusoidal at 60 hertz. So that induces, or it develops, a small noise voltage across the two different ground schemes, the two different ground points. At any rate, there's ground current flowing in that in the sleeve of the interconnecting cable. So what you can do is, instead of running that ground current and letting it infiltrate your ground pore on where all your circuitry is, right? Because if the ground pore next to all your op amps is fluctuating and has noise voltage on it, then that's going to couple into your signal path based on the output of your amplifying stages. Okay, and that can increase through the more stages you have. So instead of having it do that, this is just a very nuts and bolts way of not letting your ground current, this noise current, infiltrate this part of your circuitry. So you have a separate ground pore, and often this is done with a chassis. It's just done with the metal on the chassis instead of having a separate ground pore. This board wasn't going into a chassis, so I sort of simulated having a chassis with this ground pore in the back. And then forcing that to have to travel back out of the power input jack and back down to the wall. Instead of running through my circuitry first, or having the chance to flow over the ground plane of my signal circuitry at all, it's not allowed to get over there. So these are two separate ground pores. They're connected at one point right here between this jumper and this capacitor here. So they are at the same potential, but with this scheme, this allows me to control where noise currents flow. And a lot about low noise design is about identifying where noise is introduced in your system and diverting it. And that's through current analysis. Okay, so just remember that, so I've got a couple of different polygons here. Remember, that's done with the polygon tool. Actually, I don't know if you can type it in. You can type in draw, whoops, I want to draw a polygon, and you can draw whatever shape polygon you want to make here. Once you've done that, the idea is that you want to give it a name, and you have to name it. In my case, we'll just undo what I just did there. But in my case, I named the polygon for my signal path. If I type in info and click on the polygon, you'll notice that I named it ground. Okay, so that everything that connects with ground will connect with this polygon. This polygon fills in with all of ground, right? So so there's that, and then the one here on the back side, I gave it a different name so that Eagle would numerically associate it with a different node, and I called it physical earth. I called it PE. So I just used one of the other common ground symbols. And if you look back in my schematic, you'll see that, let's see, where, it's over here. So you'll see that I have, in fact, the DC input jack is referenced to physical earth. Here's the point where they tie together. And then here's ground, okay? And if you look at my input jacks, you'll notice that they connect to, their sleeve connects to PE. They connect to the physical earth, right? So that's how, that's the bridge between the schematic entry and the PCB design. And same thing for the headphone output. I ran the return path, the return current from the headphones to physical earth to PE. And you can see that reflected in the board easily. You look at the headphone jack on the front, and here's the sleeve, and you'll see that, okay, that's connected to the signal PE here. Whoops. All right, so so that's a bit about defining ground pores and drawing polygons. I think you've done some of that already. So why don't we take a look then at the next thing we're going to look at is the DRC. Okay, specifying the design rules in Eagle. And what are the design rules and how do you specify them? So in Eagle, you can just type DRC, or you can also go to Tools DRC. Okay, and this is where you can enter in all the different design rules for Eagle. These the rules of the specifications included are, well, you can define how many layers you want to use. So I'm using just the top and the bottom layer, and the vias, you can see the vias travel all the way through from layer 1 to layer 16. Okay, and that's what we're going to do for our designs. But if you wanted to, later on, for another project, work on, like, let's say, a 4-layer board with intermittent layers in here, you come here and change this field in the setup. It's got a little bit of a weird way of interfacing, but it gives you a lot of flexibility. For example, if they give you a multi-layer, an example of a multi-layer setup here with 2 cores, combining layers 2 and 3 and 4 and 16 respectively. You can look into that if you're interested in doing multi-layer boards. But this specifies the thickness on the copper, right? So this how much copper do you want on the top trace, or on the top plane and the bottom plane, or any traces that run on the top and bottom layers. And now that you can see you have some control over this, this is where we need to address the fact that you need to design for manufacturability, right? So depending on your needs, you might need more copper thickness on either the bottom or the top. As you increase that amount, that changes your design, the manufacturing needs and functionalities. It must meet with the board house. So often you can get information from the board house, which will specify what their criteria are for what can they design for you. And as you start to stress their design process, the cost of the boards usually go up. Okay, so we're working with a particular board house in Redwood City. They're called Bay Area Circuits, and I've gotten from them information on their minimum constraints. So we'll be using those same constraints. So you can also set constraints on clearance. So what's the minimum wire clearance? Okay, so the minimum distance between 2 wires. What's the minimum distance between a wire and a via? Right, and a via. Remember, the via is where a signal punches through from one side of the board to another side of the board, or at least more generally, from one layer to another layer. Okay, and what's the minimum distance between a pad and a via, or a pad and a pad? Okay, you don't have to worry about pads. We're not doing any surface mount components, so you won't have any pads, but you will be having vias and wire traces and things like that. Okay. Actually, I suppose you could have some pads in your design, but at any rate, you can also specify distances between copper and the drill hole. Okay, what's the minimum distances between these things? Suffice it to say, you have some control over the general placement of parts. When typically, and what this influences is the AutoRouter, but also I think this influences the. Actually, I think it just mostly influences the AutoRouter. Okay, so you also have minimum width, minimum trace width. This is a common one for board houses. They don't want to manufacture trace widths of a smaller size than, I think we were quoted from Bay Area Circuits, like 8 mils or something like that. But obviously they'd like it to be a little bit larger. So we'll probably set this to 12 mils or something like that. Minimum drill width, okay, no micro vias. Okay, so this already says here that this applies to blind vias. Okay, so those are costly to manufacture. You can make them. Those are for multi-layer designs. We won't be doing them. And this is already set that it says, well, if you put it to 9.99 mils, it means there are no micro vias. So we're good to go. All right. Now, there's a lot of things you can look at in this whole DRC tool. What's nice is that a set of specifications can be loaded into this DRC tool. So you can just load up a file, a .dru file. So if you can also, of course, you can make some changes in here, adjust things as you want, and then you can save the settings. But we already have some specified settings. I still need to look to make sure they're all right for moving to this new board manufacturer. But I have for you an engineering301.dru file. Okay, you can get other DRU files. You can save your own. As for example, SparkFun, if you've ever heard of their services, they have a .dru file that they use for a lot of their designs. You can download it and upload it and use that as your design specifications. We'll use an engineering301.dru. So that's not up on the iLearn page yet, but it'll be up really soon. So I can load that, and now we can come back here and see, okay, so like sizes. Did I not load it? Thought I loaded it. Maybe, oh, I have to hit apply, I think. Well, I thought this was already set to 12 mils. No, anyway, you know what? I think this is actually set as I think it should be 12 mils. But anyway, you're going to be able to use a .dru file that I'll just put on the iLearn page, and you can load it up. You won't have to worry about it. But you now know about what it is, and should you want to design and have some more control or various control over your design, then you can do that. Also, you're okay to change the DRU file if you make the tolerances looser, right? So don't make the board house work harder. You can make it a little looser for them. So you can increase, let's say for example, the minimum width. You can set it to, I don't know, 14 mils or something, and that'll make it larger. Okay, but you now know about that. So that was the DRC, specifying the design rules. If we want to now look at the AutoRouter, okay. So you've used this in your part 0 of the project of designing a power supply, or the power supply, and what you did mostly was just type in auto and hit OK and just let her rip and let it go. Okay. With this board, with the way that I have things placed, okay, remember I've done some very careful placing of everything. It's able to route this board with strictly the AutoRouter, just typing in auto once with 100 by 100%. So that's nice, and that's the AutoRouter is able to do that because of the way that I've placed things carefully. If I hadn't taken that consideration or that care, the AutoRouter would have a difficult time. Probably would not be able to route it 100%. But let's rip up this and look at some more of the particulars of the AutoRouter. So, for one, I want to address, I don't know, did we talk about the routing grid the first time in the first tutorial? I'm not sure that we did. So we had a lot of other things we were covering. So the routing grid is, let's just take a look. If we turn the grid on, okay, you can see a grid that's on the page here. Okay, the routing grid, and this is a grid. This is a placement grid, right? So if I want to move something, let's say I want to move R18, I'm moving it integer amounts on the grid, right? Okay, so the router has its own grid as well. And this is the grid it uses to navigate the board. Any traces that navigate the board. You can think of it like driving through a city. You can only turn where there's a street, right? So we can look in the AutoRouter, and you can specify that. And the unit is mils. Okay, that's thousandths of an inch. Okay, 50 mils is probably going to be fine for your designs. Okay, if you get to smaller, more dense designs, you can lower that. I've brought that down in the past before, working on some surface mount stuff, to about 10 mils, and the AutoRouter starts to have a pretty tough time running things around. I mean, what you should recognize is that as you decrease this number, the number of paths and choices the AutoRouter can make increases a lot. Okay, so one, you can get the AutoRouter going through a lot more decisions okay, because it makes choices on where it's going to route things. And two, you can get some really funky looking traces that are zigzaggy and take these odd paths, which you can route yourself much better manually. And in fact, in general, I usually always do a combination of routing manually and using the AutoRouter's functionality. So that's probably the most important parameter you're going to have to worry about is the routing grid. There are these other settings here which have to do with vias. You can set costs to how many vias you want, right? If you want to minimize this. This is when you're going to, you're trying to optimize your design for deployment and reduce the costs associated with your designs. In routing, you can set costs on all these things, and then there are optimizations, which in general these are all set as active. So you have 4 levels of optimization. The first level tries to optimize for this set of costs. The next one optimizes for this next set of costs. And the third and the fourth, they each do their own. So you'll see the Eagle tool, the AutoRoute tool, run through these optimizations as it routes. And you can turn them on or off. I generally, for most projects, just leave them on. And that's that. So we've looked at routing things manually a little bit. What if I wanted to use the AutoRouter to incrementally route some signals? Let's say I didn't want to route the entire board, right? So that was one of the things we were going to look at was incremental routing and ripup. And I can do that. But you know what? Briefly, I should talk about defining net classes for a moment here, okay? So let's look at that for a quick moment. So I have a bunch of signals here, a bunch of common signals in my design, and they are the power supply values and ground and things like that. Plus 15 volts and minus 15 volts runs to every amplifying chip. Ground clearly runs to a lot of places. And physical earth is another one. And so those things would be good to define as a net class because why? Well, for the power supply rails, the plus and minus 15 volt rails, I'd like all of those nets, any trace that completes those connections, I'd like it to have a larger width and maybe its own clearance. Okay, so it needs to have a width corresponding to the ampacity required for the supply rails. So you can specify that easily by defining the net class. You can access that from within the schematic or within the board. Let's go back to the board. And so I'm going to go edit net classes. And I get the list of classes I already have defined. So I've got mine defined. The default class, okay, that's all traces by default. I've set the width to 14 mils and a drill of 10 mils and a clearance of 10 mils. So now the question comes up, and I actually am not sure I have the answer for this. I don't actually have the answer for this, but I think that this overrides the DRC settings. I would think that it does, but I'm not totally sure about that. Maybe, I don't know, it'd be interesting to see if you set this to a value lower than the DRC, if the DRC would actually take over and force the trace width to be higher. But at any rate, I've set a width and a drill and a clearance for all signals in the path or in the board, and ground and plus and minus 15V and PE and power. Okay. In assigning those classes, I did have to come over to the schematic momentarily and say you can come over here and say change class. Okay, and now that I've got all these classes defined, I can choose what class I want it to be. And so I came over here and said change class to plus 15 and clicked on this guy and set it up to be that class. So you can also type in info, click on the net, and you'll see that it is defined as a plus, or it's class 2 plus 15V. You can also change what class it is right in here in the info properties window. All right, so back in the board, now that I have those classes defined, that they're named, I can use them in incrementally routing those signals. So if I want to say auto plus 15V, I want to route that signal. And you can set the auto routers, you can change the settings on incremental routing, but in general, I just leave it the same. And so I hit OK, and it routes just the 15-volt line. It also routes ground. I don't, well, I shouldn't say that it routes ground. It fills in the polygon for ground, and that seems to always happen. But it doesn't necessarily route ground. Yeah, see, it filled in the polygon for physical earth as well. Okay, so if I don't want to see that, I can type in ripup, and instead of just ripping up all signals, I can rip up ground, and then I can rip up PE. Okay, and then those are gone. And now I can see if I want to just show plus 15V, I'll type it in, show plus 15V, and there it is. Those are all the places that my 15-volt net runs to. Okay, and so it's fairly well organized. It runs kind of just where it's generated from the regulator. It runs for the most part just through the middle of the board. Okay, so that's pretty good. Most things have easy access to it. Now I can also auto minus 15V. In fact, you know what? Here, let's show that you can do both of them at the same time. So rip up plus 15V. And so I'm going to auto plus 15V and minus 15V together. And that didn't work for some reason. I might have done the syntax wrong. Yes, I think there might be a comma that was needed. Plus 15V, comma, minus 15V. Well, why isn't that working? Oh, there we go. I don't know why it didn't work a minute ago. Rip up, ground, and PE. Okay, great. So now you can see I've routed both the power signals. Okay, so let's show plus 15V, and let's just show plus 15V. It still pretty much has the same path that it did before, for the most part. And if I want to show minus 15V, that also, yeah, pretty good. I mean, I could change things at this point. If I didn't like this going up over here for some reason, I could change that. And you know, you could rip this up and just rip up only this part of the path here and say, okay, well, I didn't like any of that, and now I want to route this. I'm just going to route it underneath. Why not just, well, you know, this may want to minimize going underneath for interfering with the ground plane, but I'll do that. Why not? Just for demonstration's sake, let's say that I want to route this on the oh, I don't think that's what I wanted to do. So we'll do it from here. I'll say route and click on this guy. And it's funny, now this isn't, when you click on route, it doesn't have the default widths. So the auto router will use the widths of the net class, but you still have to specify what the width should be. And I think I use 24 mils, is that right? Yeah, it looks like the same width, right? So I will, let's see, that's not quite where I want to get it from, actually. That's still just getting it from there. But I will switch it over to, oops, not route 2. Here we go. And I'll run it on the bottom for a little while, just maybe momentarily, and then punch through to the top. Or I could just run it all the way on the bottom. That would be okay too. No, I don't know, something like that. Well, I might want to stay away from from those vias. So we'll try running it like that. Now see, that's not exactly what I wanted. I didn't want to put a via there. Ah, that's not what I want either. That's not what I wanted either. Can I delete this via? No. I want to delete the via. Yeah. So at any rate, now that I've done that, let's say I ripped up some of this, I can auto these again, plus 15V, minus 15V, and set it to go. It still didn't work. It didn't finish it. Why did it not? Rip them all up. Okay, and so we'll do okay, so we've got it. We've got it back. Okay. Now, why I wanted to show this is that in general, it's good practice to route the power supply lines before you route any signal lines. You want to try and have an optimal power distribution in general, and then route your signal lines afterwards. You want to watch out for things that could get in the way, but basically this is staying clear of most signal stuff, and so I should be okay for the most part. I will say that sometimes, if you have some signals that need to run far across the board or something like that, or there's some signals you really care about, you would route those manually as well. And you could try the auto router for it. You could also just route them manually. So I've done that on a project before, where let's say I had some inputs on the back, signal inputs on the back, and they needed to run to a control on the front, and then go back to some circuitry on the back side or something like that. I would often run them, route them manually. All right, so we've done that. I could now then route ground. Whoops, that's not what I wanted to do. I wanted to auto route ground. Okay, so I do that, and there, bang, everything is basically grounded where it should be. And remember, that's just done with these thermals connected to the via or to any holes. Right, so that's all you're basically going to see. There are no ground traces because everything is just run in the pore. Okay, and then I can auto route physical earth. Great. So this is set up. Good. I've got these tied in at the sleeves like they should be. Okay, and then I can route the rest of it. And in general, that should give you a more optimized design than just typing auto once. If you incrementally route the supplies and the grounds and then route the rest of the system, usually, in general, that's a good formula for getting a better route. Okay. All right. So let's say we're happy with this. We've saved. We've finished our layout, and now we want to look at generating Gerber files using the CAM processor in Eagle to generate the industry standard Gerber files for manufacturing printed circuit boards. Okay, so that's easily accessed in Eagle. You go to File, CAM processor. Okay, and this is the first window you'll see come up. What you want to do is load a specific job. The CAM processor can make a number of different kinds of jobs. It can process different kinds of jobs. And it depends on the type of board you're making, if you're doing a 2-layer board or a 4-layer board or a 16-layer board, and some other things. But that's one of the main things it depends on. So I'm going to open a job. All right, and Eagle comes with a few standard job files already specified. They're in the CAM folder in Eagle. And the one you want for generating all the layers and the silkscreen files and things like that is the Gerber 274x .cam, not the one with the 4-layer. So Gerber 274x is a commonly used CAM job, and basically works for the majority of board houses are ready to accept this, and their low-cost, easily manufactured boards work on this type of Gerber process. So we open that, and you'll notice that right away I've got a bunch of different jobs that this can process. Okay, and they are the component side. The component side is the top side of the board, where the components are placed, and that's the pattern for all the traces that run on the component side. So what you're going to see there, if I turn off this bottom layer, is all the traces in red. Everything in red shows up in the component file. Okay. Whoops. I wanted to go back to here. Okay. Notice, or let's just look at the other ones too. The solder side. Okay, that's the bottom side of the board. Those are the traces that run on the bottom side of the board. There are different files associated with each. The silkscreen, CMP for component. That's all your text that's on the. Keep doing that. That's all your text that's on the board. So everything that is showing in gray or white on my board is what's going to show up on the silkscreen. Well, I shouldn't say that, because it isn't necessarily true that everything that I'm seeing in the board layout is going to show up on that, and we'll talk about that in a second. You also have a solder mask or a stop mask, a solder stop mask on the component. Solder mask is the green covering that is applied to PC boards. That's not what a PC board looks like when it's first manufactured. It's just bare phenolic fiberglass board. They apply, after you run all your traces over it, they put a coat of this solder mask over the board. That's typically green. You can get them done in black and red if you've seen the Spark Fun boards and things like that. They help to isolate traces, reduce interference, things like that. They also cover up traces from being exposed, from just having metal contact them. In general, I think they're slightly covered. Anyways, you get a stop mask for the component side and a stop mask for the solder side. Okay. Notice that there's no silkscreen for the bottom side. If you wanted to specify that, you'd need a different board job. I think the 4-layer CAM job has that in there. But if you've ever seen a two-sided board that has silkscreen or text on the bottom and the top, you would need to run a different CAM job for that. Okay, so then let's look at the component side. Take a look, and you'll see that the first thing is that you can choose all the layers that get funneled into the component side. And they're set up already with this CAM job. You should be able to use this as is and be ready to go. Because all you want in the component side file is the top trace, the pads, and the vias. You want those all to turn into solder on your board. Okay, the solder side. Okay, well, correspondingly, it has the bottom traces, the pads, and the vias. Right? Makes sense that you should have solder on the bottom side of the board or the top for the pads and the vias. Right? They should have solder around them. I mean, you could specify you didn't want that. Let's say you wanted let's say that you wanted to solder only on the bottom side of the board, and you wanted no solder to be on the top on the pads. This is not a good thing. You wouldn't want to do this, but I'm just showing as an example that you have the flexibility to turn things on or off. Silkscreen. This is important. In this, you get to specify what layers you want to display in the silkscreen. So by default, the ones that are set are layer 20, dimension. Okay, that's the outside layer of your board. So when you click over here, and I look at this outer layer, which specifies the dimension, you can see that it's already set to layer 20. Okay, that has to be in your file. The board house has to have an outline of what the dimension of your part is. Okay, so you definitely want that to show up in the CAM processor. T-place shows up, T-names, and that's it by default. So let's look back at my board. What things are going to show up? Can anyone identify things that aren't going to show up based on what we just saw in the CAM processor? So the names show up, right? So let's look at that. So we'll say info, and I'll click on this R63. Name of element, R63, great. Layer, T names, layer 25, good. That shows up. That's on the CAM processor. T names is on there. What on my board isn't going to show up? So the names are going to show up. The values are not going to show up. I have the values on my board. The values layer is turned off in the silkscreen in the CAM job. In general, this is what's done in practice, is that you don't want to send your board out and it has all the values on there. People usually try to leave that off for two reasons. Maybe one, they don't want to advertise what their circuit is so much. I mean, you can read those things off of resistors and stuff like that. Two, it generally unnecessarily adds to the clutter of your design. Visually, it's just a lot more cluttered. So you can get a feel for what it would look like already just by coming over here, going onto this to the display layers, and turning off T values for the values on the top. And you can see a much neater silkscreen, right? And you don't really need those. The names, very important, really nice when you're going to populate and solder your board. You want those names on there. If you don't have them on there, you're gonna have a headache. You're gonna have your Eagle file open and constantly looking back to see what resistor is what capacitor is what, and so on and so forth. Now, if you want the values to show up because you want the luxury of just reading a value and pulling it from your parts and putting it in there, you can do that. And I'm going to leave that up to you. That being said, I do want you to, part of what you're graded on and what you should practice is designing an uncluttered layout so that your design is visually organized. Remember, as PCB designers, whether you're designing for yourself to assemble the board or somebody else to do it, you want to implement good placement and good visual clarity and cleanliness so that it's easier for the board person who's going to build the board to make it. All right, so so that's a bit on the CAM processor. If I wanted T values to show up, I would click that and put that on there, and that would be good to go. So we'll leave it off. And the other thing I want to bring up is that there are some things you can adjust here. Just leave these set as default. So you can mirror some files if you want and have them flipped horizontally. That, I guess, is useful for some applications. I haven't found need where I needed that yet. I haven't found a time when I needed that. I have accidentally done it and had some of my Gerber files mirror imaged and some of them not mirror imaged. Okay, and so that's our next thing we're going to look at is viewing your Gerber files to make sure that you've done them right. Okay, the solder stop mask. Okay, great. That's T stop, and the solder stop mask on the solder side is B stop, the bottom stop layer. Okay, so those are all those things. Back to one more thing on the silk screen, because this is a common source of confusion, is that any text you place on the silk screen, like I've got the name of this project and my name on here, right? That needs to be on a layer that is on your silkscreen as one of the choices on your silkscreen layer. In general, just use one that's going to be used already. So like this text, I have it on 51T layer 51T document. Okay, so when I go to look at the and I think that's what my name is on as well, T document. Yeah. So when I go and look at here, aha! Oh, look at that. That's actually not one of the general the first or one of the default settings on this guy on the silkscreen. So I can turn it on. I could do one of two things. I could turn it on here. Great, that would be fine. Or I could also go back to the board side and change the layer. And I could put this to, like, let's say T names, for example. Okay. I myself like to leave it as a personal preference. I like to leave it on T document so that if, for example, I go over to in the board file and I want to turn off T names for some reason, but still see what the rest of the stuff is, then my name still shows up. Or not necessarily my name, but any other text information, document information shows up on the board. I like to keep them separate. So for me, I go and either change or I save a cam job that has this whatever text layers I want to show up on the silk screen. All right, so we're gonna run with that. Notice that the file, you get the output here. It says device. Well, this is the type of output files that are going to be generated. You can see there's a lot of other kinds, but in general, people go with RS-274X. And then you get a file name, and this %n means that it's going to show up in whatever folder the project sits in. So for me, my project sits in applications, Eagle, projects. Oh, you know what? It doesn't actually. It sits in my documents in Eagle, in stereo line mixer. Okay. Now I already have. Oh no, it looks like I don't have any Gerber files in there, but I don't want them to show up in there. I actually keep my Gerber files in a separate spot. I keep them in another folder. So, you know, maybe I'll do that. I'll put them in a different one. So I'll make a new folder here called stereo mixer E301 or something. Okay, and I'll specify that I want this file to go there. So I want it to go into Documents, Eagle, and Gerber files, E301. The reason I'm doing this is that, and this %n means it's going to get the name of the board file with this .cmp. So I have to do this for each file, but this is good. Now I've chosen it for one. I can just go down the line and say this is where I want them all to go. The reason I put mine in a separate folder is that it makes it easier for me to keep track of what files are where. Now I could also just put them in their own folder inside of the Eagle projects. Like I could come to Stereo Line Mixer and put a folder in here called the Gerber or something, and that'd be fine too. I just want to keep it separate from all the board files and the backups of them. These B#1 through 9. Okay, those are backup files if you didn't know. So the .board files, Eagle by default saves 9 levels of backup. So if you do something and you want to go back to it, you've got 9 levels of revisions to go back to if you want. Same for the schematic. You can adjust that in the settings if you want. So, but we were going to go back to just here in the Gerber, and here's this file. So after I run the job, this folder should be populated with my Gerber files. So we'll do that. Instead of just processing the selection, which would do only whatever I'm on, like the solder stop mask or the silk screen, I'm going to process the entire job. So I hit process job. It says more than one signal layer is active. That's, oh yeah, I don't want that. I don't need that. That must have gotten clicked somehow. So I don't need that. So I'll say process job. Okay, and then it says, okay, collecting apertures. It's done it. What it's doing is generating high resolution files, which contain basically the numeric positioning of your stuff. And so there it is. There's my .component, .gpi, .place, .solder, .stc, .sts. I think the .place, we'll see which each of these is, but I think .place is the silkscreen. Now there's one more job you have to process, and that's the drill file. You have to generate the drill file, which specifies where to put drill holes in the board. So to do that, you open up a job, and you're going to open up the, from the CAM folder again, you're going to open up the Exelon job, which is for the drill holes. And it says, well, I've changed the Gerber 274X. Do I want to save it? No, I won't save it. So here's my generate drill data. And you can just run with what it is by default. Remember to change the file to where you want it to be. This is good. I want it in there. And you can look at the layers that it's going to apply. Well, it's just going to put the drills in the holes. So good. That's what we want. I'm going to process the job. And we're good to go. So now in my folder, I now have .drd and .dri. And these are drill files as well. Great. So we've now then generated Gerber files using the Eagle CAM processor. Last thing to do before you send these off to the manufacturer is make sure that they're right. And you use a Gerber viewer to do that. There are online solutions for this. You can load your files onto a website and it'll give you a picture of what they look like. There are tools for it. So on the Eagle page, I've given, whoops, no, I wanted this. I've given links to some Gerber viewers. So GerbV is a good one. It's freeware and it works fine. This is the link for downloading it on Windows. I have found a link that's been ported to work on Mac OS. It's a little different. I think it works a little better on Windows, but it still works fine. It works pretty well, and that's what I'm going to show you on this computer. And apparently there's one called Graphicode. I believe that's also for Windows only, and you can find other ones as well. But this is the those are the Gerber viewers, and so I am going to then open up Gerber viewer. So I'm going to type in GerbV MCN Gerber viewer, and that's who did the porting and put it together. And here it is. It's Gerber viewer. It's pretty simple. It loads Gerber files and you can view them. So since I have no files open yet, I click File Open, and I can choose. Where do I want to go? I want to go into Eagle Project Gerber files and the stereo mix E301, and let's look at the component side first. So I load the component side, and there it is. There's my components side traces. This is what the board house gets. Okay, so it's all the traces for the top side. It's got all of your traces. The pads, or the pads have been solderized, and the through holes are solderized as well. So now instead of doing open, I want to do add, because I want to add another file onto here so that I can look at multiple ones. So the DRD, now I get a DRD file, and now this is one of the things I don't like, is that the DRD file for some reason isn't showing very well on this Gerber viewer. So you might check that if you're having this similar issues. You might check that against another Gerber viewer, just to make sure. Now we can add in some other files. We can look at the DRI. I think you get an error on this one. It says, well, you can't turn that on. You can't throw that in there for some reason. It actually tells you the error on the Windows version. It doesn't on this version. So we'll add some of the other files. We'll do the GPI, which also doesn't load. Don't worry about it. The place. Okay, there's my place file, and you can see that it's got all my information on there, all my silkscreen information on there. Now I don't like that dark blue. I can barely see it. So I'll double click on this and set it to white so that I can see it and say OK. And now, oh damn it, that's not the one I wanted to do. Let's set that back to, I don't know, we'll do this color for sure. And it's, which one is it? I guess it's, oh, it's the dot place, right? I want this to be white. There we go. So now I can see the silkscreen, how that's going to look. And I can verify, okay, great. I have no values shown on here. I've just got the names. Okay, and I also verify, okay, good. These are lining up. My traces line up. I've got good registry between the files, right? That the component place, the traces, and the silkscreen are lined up. So you can run into offset problems if you had something wrong in the CAM processor. Okay, I've seen that happen before. And anyways, then you can add on some other layers. Let's add on the let's add on the solder side. Okay, there's my big solder pores on the bottom, right? And if you want to see, like you don't like where this is lining up, you want this to be above it. So I can set the place above here and the solder side on the bottom. The colors really start to change as they mix though. So, you know, where I had white before, now this is shown up as, I mean, I don't know if it's just chosen that for me. It did. I want it back to white. Yeah, so anyways, there's a couple of buggy things about this, which I'm not a huge fan of. Maybe it, taking that into consideration, you might just load all the files in before you start choosing colors for them. And the STS, don't worry about that, or the STC, don't worry about that. The STS is the, I think it's showing where all your vias and pads are going to be. So again, I'll put my place back up here above this stuff, and I'll set it to white, like I like. At any rate, you can see that everything's basically lining up. You can verify and turn various layers on or off to make sure that things are all lining up. Yes?
Is the color printed out when you set it there?
No. It has choosing the colors that you're viewing has nothing to do with the colors that they're going to give you. In general, you're just going to get a white solder mask or a white silk screen and a green solder mask, and that's it. Those are the colors. So yeah, this is simply just viewing the Gerbers. What you're going to submit to me is a zip file with all these things in it. And I'm going to submit to them a zip file of all your zip files of these Gerber files. Okay, I'll probably ask you to submit your board and schematic. I will ask you to submit your board and schematic files as well. But what's sent to the board house is strictly the Gerber files. And this is very good because it allows you the control over what shows up on your board and how your board is made. Okay. All right, so that concludes our tutorial on Eagle PCB design.